All right, we've done some work and I want to talk about uh, control systems and color shift. So today's video will star the D box, which is the lower left, lower right hand corner. It's a blue display. It goes to a customer we're going to call Mr. D. It's his box that is controlling the fire. All new algorithms or revised algorithms, and wanted to make sure it would control a fire well. So we're gonna watch this box control a fire, and we're going to discuss several things about controlling fire and measuring the smoke emissions from the fire.
254.
This is the color shift and opacity readings from the test we did with the D box, and it looks rather good. You can see the color shift as the red line, and there's a lot of debate on the utility of the color shift signal. D box controlled the fire quite well. You can see it behavior or working its magic in the video. It's hard to read those small numbers, but it's calculating how much air it's going to put into the fire and the temperature of the fire. When it inverts like that, it means that it's over 20%, and it should be doing something about that. And so it goes into mitigation mode. So the D box doesn't display the opacity or indicators from the octoring. It's simply a control system for the wood stove, displaying temperature of the wood stove and the fan control parameters. If a octoring is present, it will go into mitigation mode. That's all that. That's the way I programmed it for now, and that's the way it is. However, take a look, and it did pretty well at keeping the opacity down under 20%. We have a few excursions above, but it corrected that quickly and got it back under control. And just very interesting that the color shift comes back down to 0 after 8 hours. This is the ROR, or rate of rise, and it's one of the graphs I look at when I look at control boxes. It tells me quite a bit about the system's ability to control the fire. I like to see that it goes to 20, but not above 20. You can also see that at about 3 hours, we go negative. That means that all the fuel is consumed right around 3 hours. And after the fuel is consumed, we still pump air through the stove. It's just at a lesser rate. But a darn good looking rate of rise chart. This is the stove temperature controlled by the D box, and we did not exceed 400 degrees. That's just a nature of the fuel that I put in, but I wanted to make sure that we wouldn't exceed 475, but the control parameters appear to be adequate, and keeping the wood stove between 250 and 400 degrees is one of the goals, and it appeared to do a pretty good job. We have a tail of the fire that runs from about 3 hours out to 10 hours, so about 7 hours of tail, all producing heat into the house. I have prepared a fan signal for the D box with some analysis on it. It appears that we have about a 2.5 volt mean. That means that at any given time, we're supplying 2.5 volts to the fan. You can see several excursions above 10 volts, or right up to 10 volts. We can see several excursions down to 0 volts, but when you draw a line through the data, you can pretty much expect to get 2.5 volts. The strategy here is to always be raising and lowering the airflow to keep the flames moving across new material and to gather, combine more oxygen with the fuel. It's a strategy and it works quite well. We're going to transition from control systems to measurement. The big debate right now is, what is color shift? Just exactly what are we talking about? Well, we've got a couple ways of looking at it. One, in the chart you see here, blue is coming through less than the other colors. The sensor has 4 diodes, red, green, blue, and clear. And blue appears to be, the blue light seems to be diverted before reaching the sensor. You can see that in the chart where at 4 hours, the blue line is hanging far below the other diodes. This is a chart that I like to make, and it's called percent of max signal. So during the run, we take a look at what is the highest data point for that diode, and we plot the data as a percentage of that highest or maximum signal. That way they lay right on top of each other, and you can see when one deviates from the other, and you can see, I see anyway, that blue clearly deviates or is depressed or is not as much blue light is getting through at 2 to 8 hours, between 2 and 8 hours. That's a big time range. And we didn't put any fuel on. Let's say there's nothing on there. All the wood is consumed at 3 hours. So it's just embers for a few more hours, and we're still getting this color shift. What does that mean? What are we seeing? What is the sensor seeing? These are all questions we'd like to have answered. This is a new day of testing. It is, the testing was done on the 16th, and it's a 24-hour test. So I wasn't really going to collect any video on it. I used the yellow box for control, and I was just putting fuel on. I have a dry box that I was pulling fuel out of. At about 4 hours, 4.5 hours, I put what I call branches with a high bark content. So there were several branches that I have in a pile. It's sitting outside, and the stove was almost down in temperature, down to 200. So I had to put some sawdust on it and some flame. And you can see that it responded by going negative on the opacity. That's very interesting. It's only a few, like -1 or -2 on the opacity. And I always think that's my system drifting. However, in this case, I'm not convinced that that was what was going on. What I want you to look at is the color shift at 5 hours to 8 hours. So that's 3 hours of data. And the fuel's gone in an hour. So there's 2 hours of data where there's just embers. And look at the color shift signal. Almost 20 nanometers for at least 3 hours, all the way it takes to the next morning, the 24-hour point when I would say it had zeroed itself out. So this is very interesting that we have this long residual separation of the blue light. And, you know, if it wasn't in the data, would I believe it? Maybe not, but it's clearly in the data. It's very good data as far as there's very little noise in the signal, and it doesn't change much over time. But it by the end of the day, by the end of the cycle, after 24 hours, it did return to zero. This is the same batch of data where I focused on the 5 to 8 hours. And it's really surprising to me that the opacity signal drops below 0 and we get 20 nanometers of color shift for 3 hours. And the signal's not noisy. It's not like it's moving around a lot and we have to plot a line between all the data points. There's something that happens at 6 hours. Maybe I opened the door. Maybe I stirred the fuel. I don't remember. I didn't take notes. I didn't weigh my fuel. It's just regular burning and watching fire and staying warm that day. And wow, look at that. 20 nanometers of color shift. What's going on there? What could it be? I'd like to hypothesize, but I got greater minds working on it than I do. When I show them this data, they're perplexed as well. If I was to go out on a limb and just say, well, what could it be? I'd say it's very small particles. Very small particles. And they are bending off the blue light and not bending the red-green light. The red-green lights just go right through, yet the blue light hits those particles and it is reflected off so that it doesn't reach the sensor. So some scattering. It's a scatter, some type of scattering. And, what's the end result? What are we going to find? I really don't know, but I think it's very small particles, ultrafine particles. Maybe it's even ultra fine particles. I don't really know.